teleportation, instantly disappearing from one location and appearing at another, the ultimate transportation technology. Science fiction has promised this for generations. Beam me up. Quantum teleportation experiments claim they have done it. Some physicists say it is only a matter of time before we can teleport humans, but they are lying to you. Teleportation of any macroscopic object, let alone a human being, is not just technologically difficult, it is fundamentally, mathematically, physically impossible. And the reasons why will destroy every hope you have ever had about Star Trek becoming reality. Teleportation captures human imagination like few other technologies. The idea is simple and seductive. You step into a teleporter on Earth, your body is scanned, the information is transmitted to Mars, you are reconstructed there instantaneously. No spaceship, no travel time, just instant transportation across any distance. This is not just science fiction fantasy. Serious physicists discuss teleportation. Quantum teleportation has been demonstrated in laboratories. Photons, atoms, even small molecules have been teleported successfully. Headlines proclaim teleportation is real. Popular science articles claim we are getting closer to teleporting humans. The technology just needs to improve. Give it a few decades, maybe a century. Eventually we will achieve it. This is completely false. Quantum teleportation is not what you think it is. And even if it were, the fundamental laws of physics make teleporting macroscopic objects absolutely impossible, not just with current technology, not just for the foreseeable future, forever. Impossible in principle. Let me show you why teleportation cannot work and will never work. First, let us clarify what quantum teleportation actually is. In quantum teleportation, you take a quantum state from one particle and transfer it to another particle at a distant location. The original particle does not physically move. Its quantum state, the information describing its properties, is transferred to another particle. Here is how it works. You have three particles, Alice, Bob, and Charlie. Alice is the particle whose state you want to teleport. Bob and Charlie are entangled particles, meaning they share a quantum correlation. Alice and Bob are brought together and measured jointly. This measurement destroys the original quantum state of Alice, but the measurement outcome tells you how to manipulate Charlie to recreate Alice's original state. The state has been teleported from Alice to Charlie. This is remarkable physics, but notice what happened. The original particle Alice was destroyed. The state appeared at Charlie, but Charlie is a different particle. Nothing physical moved from Alice to Charlie, only information moved, and it moved through classical communication of the measurement result, which cannot travel faster than light. This is not Star Trek teleportation. You are not being transported to another location. A copy of your quantum state is being created elsewhere while the original is destroyed. These are fundamentally different concepts. Now let us consider teleporting a macroscopic object like a human. A human body contains about 7 times 10 to the power of 27 atoms. That is 7 followed by 27 zeros. Each atom is a quantum system with its own quantum state. To teleport a human, you would need to 1. Measure the quantum state of every single atom in the body, 7 times 10 to the power of 27 measurements. 2. Transmit this information to the destination. The information content is staggering, far beyond anything we can currently transmit. 3. Have 7 times 10 to the power of 27 atoms at the destination ready to be configured into the exact quantum states measured. 4. Reconstruct the body with every atom in exactly the right place with exactly the right quantum state. Each of these steps is impossible for fundamental physical reasons. Let me explain why. The first problem is the Heisenberg Uncertainty Principle. To measure the quantum state of an atom, you need to measure its position, momentum, spin, and all other quantum properties. But the uncertainty principle says You cannot measure position and momentum simultaneously with arbitrary precision. Measuring one disturbs the other. The more precisely you measure position, the more you disturb momentum. This is not a limitation of measurement technology. This is a fundamental law of nature. Quantum systems do not have definite values for position and momentum simultaneously. Attempting to measure both changes the system. You cannot scan a quantum system without destroying the very information you are trying to capture. For a single atom, this might seem like a minor problem, but for 7 times 10 to the power of 27 atoms, it is catastrophic. You cannot measure all their quantum states without fundamentally altering them. The act of measurement destroys the system you are trying to teleport. Some might argue that quantum teleportation solves this problem because you do not need to measure all properties, just perform the entanglement-based protocol. But this misses the scale problem. Quantum teleportation requires each particle to be entangled with a corresponding particle at the destination. You would need 7 times 10 to the power of 27 entangled particle pairs. Creating and maintaining this many entangled pairs is impossible. Entanglement is fragile. Interaction with the environment destroys it through a process called decoherence. For large numbers of particles, maintaining entanglement is exponentially difficult. The probability that all 7 times 10 to the power of 27 pairs remain entangled long enough to perform teleportation is essentially zero. The second problem is information theory and the Bekenstein Bound. The Bekenstein Bound says there is a maximum amount of information that can be contained in a region of space. For a human body with mass of about 70 kilograms and size of about 1 cubic meter, the Bekenstein bound allows roughly 10 to the power of 45 bits of information. This sounds like a lot, but the quantum state of 7 times 10 to the power of 27 atoms requires far more information to specify completely. Each atom has position, momentum, spin, internal electronic states. For a full quantum description, you need an exponentially large amount of information. The number of bits required to fully specify a quantum system grows exponentially with the number of particles. A classical description might suffice if you only care about macroscopic properties, but then you are not teleporting. You are creating a crude approximation. The reconstructed person would not have the same quantum state as the original. They would be a copy at best, not a teleportation. Even if you accept a classical approximation, the information is staggering. To specify the position of every atom to within an atomic radius, you need about 80 bits per atom. For 7 times 10 to the power of 27 atoms, that is roughly 10 to the power of 29 bits. At current data transmission rates of about 1 gigabit per second, transmitting this information would take longer than the age of the universe. And this is just position. You also need to transmit the chemical identity of each atom, which atoms are bonded to which, the three-dimensional structure of proteins, the electrical potentials across cell membranes, the contents of neurons. The information grows enormously. The third problem is the No-Cloning Theorem in quantum mechanics. The No-Cloning Theorem states that you cannot create an exact copy of an arbitrary, unknown quantum state. If you could violate the uncertainty principle by cloning a particle and measuring position on one clone and momentum on the other, gaining more information than quantum mechanics allows. Teleportation respects the no-cloning theorem because the original state is destroyed during the measurement. You are not cloning. You are transferring. But this means the original must be destroyed. In Star Trek, the teleporter disintegrates you at the origin. You are rebuilt at the destination. But the you at the destination is not the same matter. It is a reconstruction. This raises profound questions. If the original you is destroyed and a copy is created, is the copy really you? Or is it a different person with your memories? From an outside perspective, it does not matter. The copy behaves identically. But from your subjective perspective, you were destroyed. Your consciousness ended. The person at the destination is a new consciousness with your memories who thinks they are you. This is not teleportation in the sense of moving yourself from one place to another. This is death and replacement. Some might be comfortable with this, but it is not what teleportation means to most people. And philosophy aside, the physics still makes it impossible for fundamental reasons we are discussing. The fourth problem is the energy required. E equals mc squared tells us that matter and energy are equivalent. To disassemble a 70-kilogram human into pure energy releases about 6 times 10 to the power of 18 joules. That is 6 million trillion joules. For comparison, this is about 1,500 megatons of TNT, roughly 30 times the largest nuclear weapon ever detonated. Converting matter to energy and back is not a practical technology. We can do it for particles in accelerators, but not for macroscopic objects. The energy requirements are absurd. Where does this energy come from? Where does it go? How do you control it without vaporizing everything nearby? Even if you do not convert to pure energy, but instead break molecular bonds to transmit atoms individually, the energy required is still enormous. Breaking every chemical bond in the human body, transmitting the atoms, and reassembling them requires energy on the scale of hundreds of millions of kilocalories. This is not feasible. The fifth problem is timing and synchronization. To reconstruct a human, you need every atom to arrive at the destination and be placed in the correct position at the correct time. Atoms must be assembled into molecules, molecules into proteins, proteins into cells, cells into tissues, all with atomic precision. The time scale for cellular processes is milliseconds. Neural signaling operates on millisecond time scales. If reconstruction takes longer, the person is dead. Brain activity ceases. Even if you eventually rebuild the body, the person is gone. You have created a corpse. To reassemble 7 times 10 to the power of 27 atoms, each in the right place, within milliseconds, requires placing atoms at a rate of about 10 to the power of 30 atoms per second. This is impossible. Even if you had molecular assemblers working in parallel, the number required and the coordination needed exceeds anything physically realizable. The sixth problem is quantum coherence and decoherence. The brain is a quantum system. Neurons are electrochemical systems, but the chemistry involves quantum mechanics. If consciousness depends on specific quantum states in the brain, and there is some evidence it might, then teleportation would need to preserve these quantum states. But quantum states are extraordinarily fragile. They decohere on timescales of femtoseconds to picoseconds when interacting with a warm, wet, noisy environment like the human body. Any measurement, any transmission, any reconstruction process introduces decoherence. The quantum states would be destroyed long before reconstruction completes. Even if you could preserve quantum coherence somehow, you face the problem that different parts of the body would be in different stages of reconstruction. Quantum entanglement between different body parts would be lost. The global quantum state of the body cannot be preserved through a sequential assembly process. The seventh problem is thermodynamics and entropy. The second law of thermodynamics says entropy always increases or stays the same. Disassembling a human increases entropy enormously. You go from a highly organized structure to a collection of separated atoms. Reassembling decreases entropy locally, but this requires dumping entropy into the environment. The amount of heat that must be removed during reconstruction is staggering. Assembling atoms into molecules releases energy. Forcing atoms into precise positions requires removing the thermal energy that would randomize their positions. The destination teleporter would need to dissipate enormous amounts of heat, enough to vaporize any surrounding matter. Moreover, entropy considerations mean you cannot perfectly reverse the disassembly process. Information is lost to the environment. The reconstructed body will not be identical to the original at the molecular level, even if you somehow overcome all other obstacles. The eighth problem is quantum entanglement between body and environment. Your body is not an isolated system. You are constantly interacting with the environment. Photons scatter off you. Air molecules collide with you. Gravitational fields act on you. All of these interactions create quantum entanglement between your body and the environment. When you teleport, you cannot take the environment with you. But if you are entangled with the environment, removing you from the environment breaks the entanglement. The reconstructed you at the destination will not have the same entanglement relationships. You will be in a different quantum state than the original, even if every atom is placed correctly. This is another manifestation of the problem that macroscopic objects are never isolated quantum systems. They are embedded in an environment they are entangled with. You cannot extract the object from the environment without fundamentally changing its quantum state. The ninth problem is the speed of light and causality. Even if you could scan and transmit all the information, the transmission cannot be instantaneous. Information cannot travel faster than light. Teleporting from Earth to Mars takes at least 3 minutes, the light travel time. This is not instantaneous transportation. This is just a very complicated way of sending information at the speed of light. And if the transmission is slower than light, what is the point? We can already send messages at light speed using radio or lasers. Teleportation offers no advantage if it is not faster than light. But faster than light transmission is impossible according to special relativity. Causality forbids it. You cannot send information to your own past, which faster than light travel would allow in some reference frames. So teleportation is either slower than light, making it pointless as a transportation method, or it violates causality, making it impossible according to our understanding of space-time. The 10th problem is identity and continuity of consciousness. Suppose we overcome every physics obstacle, which we have established is impossible, but let us imagine anyway. You step into the teleporter, you are scanned, you are disassembled, the information is transmitted, you are reconstructed. From your subjective experience, what happens? Do you experience continuous consciousness as if you just moved to a new location? Or does your consciousness end when you are disassembled and a new consciousness begins at the destination? If it is the latter, teleportation is suicide with extra steps. The person at the destination has your memories and personality, but they are not you. You died during disassembly. A copy lives on, but you are gone. This is not just philosophy, this is physics. If consciousness is a pattern of information, and that pattern is destroyed and then recreated, is it the same consciousness? Most physicists and philosophers would say no. Consciousness requires continuity. Breaking continuity means ending one consciousness and starting another. Even if the copy is physically and informationally identical, it is not the same instance of consciousness. This makes teleportation not a transportation technology, but a copying technology that happens to destroy the original. Most people would not accept this as equivalent to actually moving to a new location. Now, there is one sense in which teleportation might be possible in principle, though still impossible in practice. If you are willing to settle for a crude approximation rather than an exact copy, you could scan a person with sufficient detail to reconstruct their general structure and memories. This is not quantum teleportation. This is classical copying. You scan the connectome, the network of neurons in the brain. You record memories encoded in synaptic strengths. You measure the overall structure of the body. You transmit this information and rebuild an approximation at the destination. This approximation would not have the same quantum state. It would not have the same detailed molecular structure. It would be you in the same sense that you today are the same person as you were 10 years ago, even though almost every atom in your body has been replaced. Continuity of pattern and memory, not continuity of substance. But even this crude classical teleportation faces insurmountable practical obstacles. Scanning the connectomy at synaptic resolution requires destructive techniques that kill the brain. We can do it with dead brains preserved for electron microscopy. We cannot do it with living brains without destroying them. And even if we could scan without destruction, transmitting and processing the petabytes or exabytes of data, and then rebuilding the body is beyond anything technologically foreseeable. So in every sense, whether quantum or classical, whether exact or approximate, teleportation is impossible. The information requirements exceed physical limits. The energy requirements are absurd. The timescales are impossible. The quantum states cannot be preserved. Decoherence destroys coherence. Entropy increases. The speed of light limits transmission. Consciousness continuity is broken. Every single aspect of teleportation violates fundamental physics. When you see headlines about quantum teleportation, remember what it actually is. Transferring the quantum state of single particles between locations using entanglement, not moving objects, not transporting people, not Star Trek beaming, just a clever quantum information protocol that respects all the limitations I have described. Teleportation is a fantasy. It will remain a fantasy forever, not because our technology is insufficient, but because the laws of physics forbid it. The universe does not permit the kind of information processing, energy manipulation, and quantum state preservation that teleportation would require. You will never be teleported. No one will, ever. The physics is absolute on this point, and recognizing this is not pessimistic. It is realistic. It is understanding the limits that nature imposes. We have other options for transportation. Spacecraft, fast spacecraft, eventually maybe relativistic spacecraft. We can send information at light speed, which effectively allows us to project our presence across vast distances through communication and remote operation. We can upload minds to computers if consciousness is substrate independent, though this too is speculative. But teleportation in the sense of disappearing here and appearing there, intact and alive, with your consciousness continuous? Impossible. Forever. And that is just how physics works.